Hi, I'm Roland Minton. These are some of my favorite math stories. In this episode, mathematics is highly ranked. We'll look at one way that mathematics can be used to rank sports teams. Linear algebra is arguably the most variable of courses for undergraduate math majors. By that, I mean that what you get in the course is highly dependent on who teaches it. Linear algebra can be highly theoretical, or extremely applied, or anywhere in between. The ranking system we explore here is one of the interesting, to me anyway, applications that are readily available to linear algebra students. Sports leagues almost always have year-end playoffs to determine their champions. The playoff matchups, in turn, are determined by how the teams are ranked after their regular season games. For example, maybe only the top 8 teams qualify for the playoffs, with number 1 playing number 8 in the first round, number 2 versus 7, 3 versus 6, and 4 versus 5 rounding out the schedule. One difficulty is that typically the teams do not play equivalent schedules. Team A could be better than Team B, but have a worse record if Team A played the best teams and Team B played the worst teams. This is especially problematic in college sports where the schedules are small and varied. So the challenge is to use a season's worth of results to rank teams from first to last. A small example will show one way to accomplish this. Suppose there are just 4 teams in our league. We'll call them A, B, C, D. We'll first rank them by rating them. If that doesn't make any sense, here are the definitions. A ranking lists the teams in order of ability. For instance, A first, B second, then C and D. A rating assigns a number to each team, summarizing its ability. For instance, A's rating might be 8 and B's 6. You can see that A ranks first, B second, then C and D. You can also see that A and B are relatively close together, with a larger drop down to C and D. The first step in finding a mathematical rating is to set the rules, carefully defining what you want the rating to accomplish. The rating system we develop here starts with the idea that the team ratings, we'll use lowercase letters for them, should represent points, so that A equals 8 and B equals 6 means that we think A is 2 points better than B. We also need to precisely describe how the team results will produce the ratings. This should be consistent with our points interpretation. Now, if on the average for the season, Team A is 3 points per game better than its opponents, we want A's rating to be 3 higher than the average of its opponents' ratings. For example, if A plays 4 games, scores 40 points while giving up 28, A has outscored its opponents by 12 in 4 games, an average of 3 points per game. To turn this into an equation, we need to know which teams A played. Let's say it played B twice and D twice. Then the average of its opponents' ratings would be B plus D divided by the 4 games to average the opponent's ratings. And we want A's rating to be that average plus 3. As an equation, A equals 2B plus 2D divided by 4 plus 3. This assumes a really nice form if we multiply by 4. 4A equals 2B plus 2D plus 12. Reading this equation, we can see 4A says A played 4 games, 2 of them against B, 2 of them against D, and outscored its opponents by 12. That's nice. Before continuing on, let's note a couple of features of our model. A's rating will depend on its opponent's ratings. The better the teams A played, the larger the average opponent's rating will be, and hence the larger A's rating will be. So strength of schedule is built into the model. Also, the more points A scores, the better its rating will be. Back to the model. We have an equation for A. Each team gets its own equation. Let's say that teams B and C each played 4 games, scored 32 points, and gave up 30 points. Sounds like B and C are tied, doesn't it? Let's also say that B played A twice and C twice, C played B twice and D twice, D scored 24 points, gave up 40, played A twice and C twice. For B's equation, its net points are 2, so for B played 4 games, 2 against A, 2 against C, plus 2. Similarly, for Team C, we get the equation 4C equals 2B plus 2D plus 2. And for Team D, we have 4D equals 2A plus 2C minus 16. D got outscored by 16 points. So all of these equations together makes a nice linear algebra problem. You may have seen this referenced as 4 equations and 4 unknowns in an algebra class. In linear algebra, this is a system of equations to be solved using matrix techniques developed in the course. One of the questions in a linear algebra course is how many solutions this system has. Interestingly, the only possibilities are 0, no solutions, 1, a unique solution, or infinity, an infinite number of solutions. For our problem, there are infinity, which might be discouraging. Which rating do we want? As it turns out, one solution is A equals 5.25, B equals 4.5, C equals 2.75, D equals 0. Here's another solution. Do you notice any pattern here? That second set of solutions is the same as the first, except each rating is 10 larger. Crucially, adding 10 to all numbers doesn't change the ranking, A, B, C, D, regardless, or the difference between teams. A is 0.75 better than B, 2.5 better than C, 5.25 better than D. All solutions are equivalent for our purposes, so just pick one, such as the 5.25, 4.5, 2.75, 0. I still think it's cool that even though there's not just a single solution, all solutions give us the same information. Let's talk about that information. Why are B and C rated differently even though their results are identical? They did have identical point differentials, but they played different schedules. B played the best team A twice, while C played the worst team D twice. Strength of schedule matters. There are numerous tweaks that can be made to these ratings. For example, sports fans will object that this is all about points and not about whether A wins its games or not. To use wins, just record every game as 1-0. 1 point for a win, -1 for a loss. Or do both points and wins and average them together. This is what I do in my system that I call by the numbers. The system can be adapted to any sport that keeps score. There are many rating systems that start from different models. See the excellent book, Who's Number One? The Science of Rating and Ranking by Langville and Meyer, or Google mathematical rating systems. Maybe you'll win the next March Madness pool.